An electric kettle needs 6 minutes to boil 2 kilograms of water from an initial temperature of 20 degrees Celsius. The total cost of electrical energy required is 12 cents, and the rate that you're being charged for that energy is 40 cents per kWh. Find the kilowatt rating and the overall efficiency of the kettle. So this is putting together a lot of the previous unit conversions and calculations and energy calculations, along with some new information, which is this rate, 40 cents per kWh. I wanted to do this because connects maybe an experience you've had. Maybe you've paid an electric bill, and electricity is billed in cents per kilowatt hour. 40 cents is pretty high, by the way. Usually it's like 13 to 20 cents per kilowatt hour. Alright, let's get to it though. Given we have 2 kilograms of water. Kilograms is a mass, which has the symbol M, 2 kg. We were told the initial temperature, so before we turn the kettle on, the initial temperature, T initial, was 20 degrees Celsius. So the total cost of electric energy was 12 cents, so we're going to pay 12 cents. We don't really have a symbol for that in this class. 12 cents, that's looks like this, right? You don't use that symbol too much anymore. 12 cents. And then the rate. We didn't have a symbol for rate either, but that's 40 cents per kilowatt hour. 40 cents per kWh, right? When you see the word per, that tells you that's a division. So what are we asked to find? KW rating of the kettle. What is a KW? That's a power rating, so we're trying to find the power of the kettle. Right. Is that a 50 watt kettle? Is it a 20 watt kettle? What is it? What is the power rating of a kettle? You might not have an idea. And then we're also asked to find efficiency. That's eta. Okay, so those are kind of two related problems. Find the power of the kettle and the efficiency right there. So the solution. So the formula we have for power is energy is equal to power times time, which we've been converting over to power is equal to energy divided by time. We were given time up here. Ooh, I forgot to write that down. Glad we did this. T equals 6 minutes, right? An electric kettle needs 6 minutes. So the time was 6 minutes down here, but we weren't directly given energy, right? There's no E showing up here. Kilowatt hours is our energy unit here, but it's embedded in this fraction. And so what we want to demonstrate is how do you back calculate how much energy was used. If you paid 12 cents total for the energy you used, and you were charged 40 cents for every kWh you used, you can kind of see you didn't use a full kWh here, right? A full kWh would have cost you 40 cents. We didn't pay that. Paid less than half of that actually, so we need to figure out how much that is. So what we know is that the total cost in cents is going to be equal to the rate times the total energy used. And if we were to set that up, we'd say 12 cents is equal to 40 cents per kWh times the energy that was used in the system, right? So 12 cents equals 40 cents times energy. And I'm just going to convert that over to say energy is equal to, we're going to divide left and right, 40 cents divided by 1 kWh. So the cents are going to cancel. kWh is down here in the numerator, in the denominator of the denominator, which is going to pop it up into the numerator, so it's equal to 12 over 40 kWh right there. So we can simplify that and we get 0.3 kilowatt hours. We use 0.3 kilowatt hours to boil water, right? So that tells us how much energy was used. Now we can plug that into this formula here. Power is equal to energy divided by time is equal to 0.3 kWh divided by time, which was 6 minutes. Oops. Okay, so we need to realize that hours aren't going to cancel here, and we need to either convert kilowatt hours over to kilowatt minutes or minutes over to hours. I'm going to do the latter. 1 hour is 60 minutes. So now my minutes canceled, my hour cancels, and I'm just left with kilowatt. So 0.3 over 6 over 60 kilowatts. So if you do that math, you get 6 divided by 60 is a tenth. 0.3 divided by a tenth is 3. So 3 kilowatts is equal to the power of the tea kettle. So I can tell you what the power of the tea kettle is by knowing how much energy it used over a certain amount of time. So that's the first part of the problem. The second one was, well, what's the overall efficiency of that? So remember, efficiency is defined as the usable output energy divided by the input energy. We already calculated input energy is equal to E out over 0.3 kilowatt hours, right? But where do we get E out? Where does that come from? Well, the usable output of the tea kettle is, of course, the energy that was imparted into the water, and we were told that it was boiling, right? And we were given a formula in the textbook, or maybe you've taken this in a Physics 1, or maybe this would be Physics 2, but the energy stored in a mass of water to change it from one temperature to another is the mass times C sub P, which stands for specific heat, times the change in temperature. So the temperature final minus the temperature initial. And so we were told that there was 2 kilograms of water. In the textbook we talked about specific heat. Remember, that's how much energy is necessary to put into a fluid to raise 1 kilogram by 1 degree. And that's specific to the material, so you got to look that up in a table of different materials. 4190 joules for every kilogram degrees Kelvin in is the specific heat of water. And then we need to multiply by the change in temperature. We weren't told what the final temperature was, but it's a kettle that's boiling water, so hopefully you know that's 100 degrees Celsius minus the initial temperature, which we were given as 20 degrees Celsius. So that's going to be 80 in there. You might freak out and say, oh, Kelvin and Celsius don't directly cancel, and in fact they do. So that's not a problem for us. So if you're not familiar with that, I encourage you to look up temperatures and see how that actually cancels out. But if you do the math, you're going to get 0.186 kilowatt hours is the amount of energy that's stored in that boiling water, that 2 kilograms of boiling water. So now we can calculate the output efficiency of our tea kettle system. That's going to be 0.186 kilowatt hours divided by 0.3 kilowatt hours. And then we want to express that as a percentage usually. It's kind of up to your preference, but I like to. So this kettle is a nice 62% efficiency. So not too bad of a kettle.